Emergence is a fascinating phenomenon observed across various scientific disciplines, where simple, localized interactions give rise to complex global patterns and behaviors that cannot be directly inferred from the individual components alone. This analysis explores the concept of emergence through the lens of the causal triad, elucidating the pathway from local rules to global patterns, emphasizing the crucial transitions and interactions that underpin emergent phenomena. At the heart of emergent systems are local rules, the foundational principles governing individual entities within a system. These rules are typically straightforward, applying uniformly across all components. Despite their simplicity, when these rules are executed, they initiate interactions among entities, leading to complex interdependencies. Stephen Wolfram, a pioneer in cellular automata, highlights the power of simple rules in generating complexity. He states, "Even very simple rules, when iterated, can produce incredibly complex patterns." This insight underscores the first link in the triad, where the application of local rules leads to intricate interactions among system elements. In essence, individual actions, governed by simple rules, give rise to complex interdependencies, setting the stage for further complexity. The interactions generated by local rules do not exist in isolation, they intertwine to form complex dynamics within the system. Through scaling and collective behavior, these dynamics culminate in global patterns. These emergent properties are not directly predictable from the initial rules, representing a new level of order and complexity. Philip Anderson, in his seminal paper More is Different, articulates this transition beautifully. The ability of the whole to be more than the sum of its parts is the most striking property of complex systems. Anderson's perspective aligns with the second link of the triad, where interactions among components, governed by local rules, aggregate into global patterns. This emergence of new properties exemplifies the transformation from micro-level interactions to macro-level phenomena, illustrating how higher-order complexity arises from simpler interactions. The absence of local rules leads to the absence of emergent global patterns. This negative causal pathway highlights the indispensable role that local rules play in the formation of structured interactions and emergent behaviors. Without these foundational rules, the intricate patterns characteristic of complex systems cannot develop. Murray Gell-Mann, renowned for his contributions to particle physics, emphasizes the necessity of underlying rules for coherent structures to emerge. He posits, without the rules, there are no intricate patterns. This assertion aligns with the negative pathway in the triad, underscoring that without foundational rules, the structured interactions required for emergent behaviors cannot form, thereby preventing the development of complex global patterns. The thoughts of leading scientists like Stephen Wolfram, Philip Anderson, and Murray Gell-Mann provide a deeper understanding of the causal triad in the context of emergence. Their insights help elucidate how simple local rules lead to complex interactions and ultimately to emergent global patterns. Wolfram's work on cellular automata underscores the first transition, simple local rules leading to complex interactions. His observation that even basic algorithms can generate complex behaviors supports the idea that the foundational rules governing individual entities are pivotal in initiating intricate interactions within a system. Anderson's concept of more is different captures the essence of the second transition, interactions culminating in global patterns. His assertion that the whole can be more than the sum of its parts highlights the emergent properties that arise from the aggregation of local interactions, reflecting the unpredictability and novelty inherent in emergent systems. Gell-Mann's emphasis on the necessity of rules aligns with the negative causal pathway, the absence of local rules leading to the absence of global patterns. His insights reinforce the idea that without foundational rules, the structured interactions necessary for emergent behaviors cannot form, preventing the development of complex global patterns. The causal triad provides a robust framework for understanding the phenomenon of emergence. By examining the transitions from local rules to interactions and from interactions to global patterns, we gain a clearer understanding of how complexity arises from simplicity. Insights from prominent scientists further enrich this understanding, emphasizing the transformative power of local interactions in generating emergent phenomena. This model underscores the unpredictability and novelty inherent in emergent systems, where new properties manifest at higher levels of organization. Understanding these principles not only deepens our appreciation of emergent systems, but also reinforces the interconnectedness of elements within complex systems, paving the way for advancements in fields ranging from physics to computer science.